Greetings! Welcome to the fourth lecture on noise. I am Behzad Razavi. In this lecture, we will talk about noise in basic amplifiers and see how we can analyze the effect of various sources of noise in a given circuit topology. So, in this lecture, we'll talk about noise in various stages. And these stages include the basic stages that we have seen in analog design, including the common source amplifier, the common gate amplifier, source followers, and cascodes, and eventually differential pairs. Using these building blocks and understanding their noise will help us with larger circuits such as op-amps, etc., that we will see in the next lecture. Okay, so before we start, I would like to refresh your memory about a few concepts that we covered in the last lecture. One was a procedure for analyzing noise in a given circuit. And we went through these steps. We said that first we identify all sources of noise in the circuit. Then we find the transfer function from each noise source to the output. And then we can find the noise contribution at the output from each of these sources by multiplying the spectrum of this source by the magnitude squared of the transfer function from here to here. So we repeat this for all sources of noise and we obtain the contributions at the output. And then if we know that these sources are uncorrelated, we simply add the spectra at the output and that will give us the total noise spectrum at the output of the circuit. So that's how we go about calculating noise in a given circuit topology. All right, and then we also talked about the concept of input-referred noise. We saw that if we just look at the output noise, that noise will depend on the gain of the circuit. So two circuits that have different gains may have the same output noise, but that's not a fair comparison between them because they will have different signal levels at the output. So we decided to refer the noise back to the input where it corrupts the input signal directly. And we saw that in general, we need two types of input-referred noise components. One is a voltage source, and the other is a current source. And our calculation was as follows. For the voltage noise, we short-circuit the input port of the circuit, and we have a certain amount of noise at the output. Now, if the input-referred noise voltage is to represent the noise properly in this case, then what we should get by applying this input-referred noise to a noiseless copy of the circuit should give us the same output noise as what we had here. So we find the output noise, we divide it by the gain, that will give us the input-referred noise voltage. And for the input noise current, we go to the other extreme and we leave the input open and we find the output noise, which may not be the same as the previous case. And then we say that if this noise current is representing the behavior correctly in this situation, then the output noise of this noiseless circuit should be the same as the output noise of this noisy circuit in this condition. So from this, we can calculate how much noise current we have. In a sense, it would be the output noise measured here divided by the transconductance squared of this overall circuit to give us the input-referred noise current. Now, we saw a very simple example of applying these ideas. In particular, we saw that if we have a common source stage and we are interested in its thermal noise, we have an output noise given by 4 kT gamma GM, which is this noise current spectrum, times the transfer function, which is just RO and then squared. And we said that, okay, we're going to refer this to the input by dividing it by the voltage gain squared, which is GM squared RO squared. And that gave us a certain amount, 4 kT gamma over GM, for the input-referred noise voltage spectrum. Okay, so that's great. We can use this to determine how noisy the circuit is and how much it corrupts the input signal as it arrives. But we also have a point of curiosity here. we saw that for this particular case of a common source stage, the noise in the channel could be referred to the gate as a voltage source with this amount of spectrum. Now the question is, if I have a transistor somewhere in any arbitrary circuit, can I perform the same transformation for it? Even though it may not be a common source stage, its source may not be grounded, etc. So we will go and look at this general circuit and see what we can observe. All right, so here's a transistor in a general circuit connected to nodes 1, 2, and 3. Let's not worry about body effect. And we have this noise current going from the drain to the source terminal. Now, we are wondering if this circuit can be transformed to this circuit where the noise of the transistor is modeled by a voltage source in series with the gate. And if that's the case, then how much spectrum do we have for this guy in terms of that? Okay, so this can actually be proved. And to prove that, first of all, we assume that node 3 is a reference point, reference voltage. You can call it ground, even though this node may not be the actual ground of the circuit. Just imagine that we are measuring all of the voltage in the circuit with respect to node 3 in both cases. All right. Now we also notice that node 1 may have some noise in it arising from M1 if there is any feedback path this way or this way. So node 1, the voltage at node 1 is not necessarily noiseless, even though everything else in the circuit is noiseless. Okay, now we say, how much is the total current that we have here? Well, the total current that we measure here is equal to this current plus any current that is generated by M1 itself resulting from a time-varying VGS. And that would be V1 times Gm. That's one current that this transistor is generating, because V1 may not be zero. Remember, there might be noise in there. And then we have the noise current of the transistor itself, so these two flow here. Okay, I said V1 times Gm, not V1 minus V3, because 3 is my reference point for the entire circuit. All right, so the total current that flows is Gm times V1 plus In. Why did I write these as voltage and current quantities, not as squared quantities, as spectra? This is because V1 and In are definitely correlated, right? V1, the noise in V1 comes from In, somehow through some feedback or something, right? So we just have to keep it like this. Okay, now let's go to the circuit on the right-hand side and ask ourselves, how much is the total current here? Well, we are assuming that M1 itself is noiseless, and we are hoping that the noise of M1 can be modeled by a voltage source. So there is some voltage here called Vn. There is still noise in 1, perhaps, because there might be feedback. So the gate voltage is equal to V1 plus Vn. And that gets multiplied by Gm to produce this current. Again, we don't have to subtract V3 because node 3 is the reference point for all of our voltages. So the total current that we measure here is GmV1 plus GmVn, because the voltage here is V1 plus Vn. Okay, so if I compare these two, I can see that this current will be the same in the two circuits if GmVn is chosen to be equal to In. Of course, you may say, how do we know V1 is the same? And it turns out that V1 is the same, considering that the gate current here is 0. It has to be the same in both cases. Okay, so our conclusion is that these two circuits are equivalent, meaning that the circuit doesn't feel that we took this current source out and replaced it by this voltage source if GmVn is equal to In. In is the noise of this guy, and Vn is what we are putting in here to represent that noise. Now, these are random quantities, so the only way they can be equal is if their spectra are equal. So we say that the spectrum of In is equal to the spectrum of Vn times Gm squared, and that gives us Vn squared bar is equal to 4 kT gamma over Gm. Just like what we had before in the simple common source stage without degeneration. So generally we call this the gate referred noise voltage of a MOSFET. And what's interesting is that it doesn't matter what we have down here or up here, it's always true, provided that this current, the gate current, is 0. Okay, so now that we have that clarified, we can go ahead and analyze noise in different stages. Now, whether we want to model the noise of a transistor by a current source between drain and source or by voltage source in the gate depends on the circuit. Sometimes one is easier than the other. Let's look at a common source stage. Here's a transistor with a load resistor. Our first step in the analysis procedure is to identify all sources of noise. Okay, so we have some 1 over F noise from M1, some thermal noise from M1, and then some thermal noise from RD. And again, this can be modeled by a voltage source if you want. And this can also be referred here as a voltage source if you want. Those are all possibilities. It doesn't really matter too much here. Okay, so let's try to find the output noise voltage. And then once we do that, we can refer it back to the input by dividing by the gain squared of the circuit. This current is 4 kT gamma Gm, and this current is 4 kT over RD. Both of these currents add up and flow through RD. The transfer function from these currents to the output is RD squared, RD, so the square of that would be RD squared. So we have 4 kT gamma Gm times RD squared. Then we have 4 kT over RD times RD squared, which is of course 4 kT RD, assuming that channel length modulation is neglected. And then we also have the 1 over F noise of the device, and the transfer function from here to here is minus GMRD, so we have to square that. So that would be our 1 over F noise spectrum multiplied by Gm squared, RD squared. So that is the total noise voltage that we measure at the output. Now we're going to take that and divide it by the gain squared, which would be Gm squared RD squared, to refer to the input. So the input is given by this expression. We divide by Gm squared RD squared, and that is the final result. Okay, so let's eyeball this a little bit and see what kind of intuition we can gain from this very simple result. All right, so this simple result says that the input referred noise voltage of a common source stage is given by 4 kT gamma over Gm. What is that? That is the gate referred noise voltage that we just talked about. So it makes sense. If I had modeled this noise by gate referred noise here, it would be right at the input. I wouldn't have to take it to the output and bring it back to the input, right? Because by going from here to here, we multiply by the gain squared, and then by going back from here to here, we divide by gain squared. So then there's no reason to take it out, to take it to the output. We could just keep it at the input. So it makes sense that 4 kT gamma over Gm appears as that value with a coefficient of 1 because it is a voltage source right at the input of the circuit. Similarly, the flicker noise. So we see that the flicker noise was multiplied by the gain squared, but then got divided by gain squared, so it came back as it was before. So again, if we have enough understanding of the circuit, we can take some shortcuts. We can say, well, this noise and that noise actually don't have to go to the output. I'll just keep them at the input, and all I need to do is find the noise of this guy at the output and then refer it back to the input. Okay, and the last component that we have here is 4 kT over Gm squared RD. Now what is that? Well, I can think of it this way. 4 kT over RD is the noise current injected by RD into the output, right? This noise here. Now, I could try to refer this back to the input if I know the relationship between the output current of the circuit and the input voltage. I know that the output current of the circuit is equal to Gm of the transistor times the input voltage. So if I want to go from the output current back to the input voltage, I just need to divide by Gm. And if I have the spectrum of a noise current, I have to divide by Gm squared. So this term is really just the noise of Rd, noise current of Rd, divided by Gm squared, so that it becomes the voltage at the input. And that tells us that we have this relationship for these different components in terms of the input referred noise of the common source stage. All right, now from these we can also have some guidelines to minimize the noise of such a stage. So here are some general observations that we can make. Okay, so look at these terms. Of course, we want to maximize the Gm of the transistor for minimizing the thermal noise contribution. Interestingly, that also reduces this contribution, so that's great. For maximizing Gm, we have two possibilities: increase the bias current, which translates to a higher power consumption, or increase W to maximize Gm, and increasing W increases the capacitances of the transistor. So we have a simple trade-off between the input referred noise, the input capacitance, and the bias current and power consumption of the circuit. Now, for the 1/f noise, as we saw before, the only solution is to increase the channel area, and that means the channel capacitance. So we have a simple trade-off between the noise of the circuit and the input capacitance of the device. One other possibility to minimizing this term is to maximize Rd while everything else is constant. So if I try to increase Rd while the bias current is constant, then what happens? Well, if VDD is constant, this voltage comes down. If we want to keep this voltage constant, then we have to raise VDD to accommodate a larger Rd. We just have Ohm's law. Rd times Id is the voltage that we have here. So that voltage has to be accommodated by the supply voltage. So we say that as Rd increases to reduce this noise, either the supply voltage has to go up, or we have to lose voltage headroom, meaning headroom available for voltage swings at this node. Neither of these are desirable. So that's a trade-off that we face between reducing the noise contribution of Rd and reducing the headroom or increasing the supply voltage. All right. Now, if this term is bothersome, we can have a remedy. So this load resistor is here really just to provide the bias current for this device. Now, I'm looking for a load that does not have this limitation of this voltage drop, which is given by Rd times Id. In other words, I'm looking for a load that does not satisfy Ohm's law. And such a load would be a transistor, a MOS transistor, operating in saturation. So I can replace Rd with a current source realized as a PMOS device. And we know that this VDS can be relatively small, certainly smaller than Rd times Id for a given voltage gain, etc. So this allows us to accommodate a larger voltage swings here for a given amount of bias current. So now what happens to the noise performance? Well, we don't have the noise of Rd as kT over Rd, but now we have the noise of M2. And if we just focus on thermal noise for now, the noise of M2 is 4 kT gamma GM2, represented by this current source. And the noise of M1 is 4 kT gamma GM1. Both of these have to flow through an impedance here, which is the parallel combination of these output resistances. So we end up with a certain amount of noise, and then we have to divide that by the gain squared. The gain is GM1 times RO1 in parallel with RO2. When we do that, we end up with this equation here. So 4 kT gamma over GM1 is to be expected. That's the gate referred noise of this transistor. And then we have 4kT gamma GM2 over GM1 squared. That makes sense, right? Because this is the current noise produced by M2, just the way we had 4kT over RD as the current noise produced by RD, which has to be referred to the input, so it has to be divided by GM1 squared. So that's why we have this here. Okay, so this circuit and this result tell us that to improve the noise performance, we have to maximize GM1 and or minimize GM2. So this device needs to have a high GM, maybe a wider device, a smaller overdrive. This device needs to have a low GM, so maybe a larger overdrive if we can accommodate it in the supply voltage. Now, is this noise higher or lower than the thermal noise of this stage? They are probably comparable. But what's worse in this case is that now we also have to deal with the flicker noise of M2, whereas here RD did not have flicker noise. So that's one trade-off that we face when we go from this stage to this stage. Okay, now, so what we see in this interesting topology is that M2 acts as a constant current source and M1 as an amplifying device. And as such, M2 does contribute both thermal noise and flicker noise. Now, is it possible to improve the situation by letting the signal flow through M2 as well as M1? And that would be something like this. So the signal comes in and it goes to the gates of both devices. Now you can see that M2 and M1 from a small signal perspective are in parallel. The drains, the gates, the sources are shorted, so we can consider as one transistor. And that means that the input referred thermal noise is just 4kT gamma over the overall transconductance, which is GM1 plus GM2. So you see that this circuit has a much better noise performance than the previous circuit because we have actually exploited GM2 to reduce the noise rather than to increase the noise. So this is a good circuit. You can see it resembles a CMOS inverter, except that M1 and M2 are always in saturation. But the biasing is a little more complicated. So first we need to establish the right gate voltage and also the right drain current. So for example, if we connect a feedback resistor from the output to the input, and it's a large resistor, we can ensure that these two DC voltages are equal. And that's good because then that keeps both of them in saturation. But then the current of the circuit is not well defined because if the supply goes up and down, the VGS of both of these devices changes. So we place a constant current source here to bias both of these, and then place a large enough capacitor from here to ground to make sure that M2 is not degenerated by anything significant, so that M2 still acts as an amplifying device. And if the DC coming here is different from the DC that these 2 points want to have, you also have to have AC coupling at the input to make sure that everything is well defined and independent of the preceding stage. So that's a good circuit for low noise applications, and it has some other nice properties as well. Okay, let's go to the common gate stage and talk about that briefly. We'll just focus on thermal noise for simplicity. A common gate stage has a low input impedance, so we suspect that we also have to worry about the input referred noise current. So we run the tests that I showed you before. We apply noise voltage here, we apply noise current here. In one case, in a sense, the input port is shorted here. In the other case, the input port is left open. And based on these calculations, we can find the input referred noise voltage and the input referred noise current. The input referred noise voltage is given by this expression. Here we have GM plus GMB because there's some body effect. But for a moment, don't worry about body effect. And what you see is that 4kT gamma GM over GM squared is in fact 4kT gamma 4kT gamma over Gn, which is the same as that of a common source stage. After all, we have a gate-referred noise voltage source here, which can be just transferred to the input. And then we also have 4kT over Rd over Gm squared approximately, and that's what we saw before as well. So the input referred noise voltage of a common gate stage is quite close to that of a common source stage. But there's also an input noise current. So when we calculate the noise current of this circuit, it comes out to be just 4kT over Rd. And that makes sense because the current gain from here to here is 1. So whatever noise current we have here, it just refers to the input. Okay, this becomes problematic in some circuits. For example, if you design a transimpedance amplifier for optical communications where the input noise current is critical, this becomes an important issue. All right, now in practice we also have to bias up the common gate stage, for example, by a current source, such as this. This is a current source coming from a current meter arrangement, and it turns out that the noise current of M2 adds directly to this value here. So, and this noise may not be negligible in general, so we have to worry about not just 4kT over Rd, but also the noise current of M2. The noise voltage is not affected by this transistor. Okay, let's talk about source followers. I'm assuming that we have a source follower device M1 and we have biased it by a current source M2. These are just AC grounds here and here. And we have some noise from M1, some from this device M2. Let's just assume again thermal noise for now. And if you write it out, this equation actually is familiar. This is the input referred noise voltage of this circuit, which we saw before. And it just happens to be the same for the source follower. So does it mean that these two are equally good in terms of noise, low noise design? No. The difference is that a source follower doesn't have any voltage gain. So any circuit that comes after the source follower will have to have extremely low noise. Whereas this circuit has voltage gain from here to here, maybe a gain of 5. So whatever comes after this circuit doesn't have to have as low a noise as this circuit. So that's why in general we don't like source followers in the signal path, because they just add noise and they don't do anything. They don't amplify. So in low noise design we try to avoid source followers as much as possible. Okay, a few words about the cascade structure. Here's the cascade structure, and first let's focus on the noise of M1 and Rd. Well, what we can see is that if I model noise of M1 by a current source, that current mostly flows to the output node, right? You have a current flowing from here to ground. Where does it go? It comes from M2. A slight amount of it is lost to the output resistance of M1, but we don't worry about it. And then the noise of Rd also flows to the output node. So we see that as far as the noise of Rd and the noise of M1 are concerned, the output is similar to that of a simple common source stage, right? Because both of these noises are flowing to the output node. So as far as these two contributions are concerned, we can say that the input referred noise is just 4kT gamma over Gm1 plus 1 over Gm1 squared Rd. Okay? In fact, this we could have predicted because we know that the noise of M1 can be represented by an input referred, gate referred noise anyway. So that would be easy to see. Okay, so for M1 and Rd, the noise performance is similar to that of a common source stage. What remains is the noise of M2. So how much does M2 contribute? Well, this time we model noise of M2 by a gate referred noise source, and we are wondering how much of this noise goes to the output. Okay, Well, this looks like a common source stage, right? The noise is going to the gate of the device, and we are interested in the drain voltage. Except that this common source stage is heavily degenerated by M1. If M1, for example, has an output resistance, then the resistance from here to ground is RO1. So there's a very large amount of degeneration, meaning that the gain from here to here is very small, probably less than 1. So the gain that VN2 experiences as it travels to the output is definitely much less than the gain that the voltage source of this guy would experience as it travels to the output. So that means that the noise contribution of VN2 is definitely much smaller than the noise contribution of M1 and its associated voltage. Right? So in general, we say, in a well-designed circuit, in a well-designed cascode, the only contributors should be the input transistor and the load, but not the cascode device. The only exception is at very high frequencies, where this capacitance to ground produces a lower impedance, so it allows this noise voltage to partially be amplified. But that rarely happens in actual designs. Okay, the last stage we're going to talk about is differential pairs. So here's the differential pair with all the usual suspects in it. We have shown you all the noise voltages and so forth. And we can calculate each of these, the contribution of each of these to the output, and carry out all the necessary steps that I showed you before. And what we see at the end is something like this. So this term represents the thermal noise behavior, and that the 1 over F noise, as they are referred to the input here. So we can see that we have 8 kT gamma over GM. Why? Well, we have 4 kT gamma over GM for this, 4 kT gamma over GM for this, and these two are both in series with the input. So they have to add up, and they're uncorrelated, so their spectra have to add up. So that gives us a factor of 2 here. Then we also have the contributions of RD. So it's 8 kT over RD over GM squared. Why? Again, because we have 2 resistors, their noises are uncorrelated, so when you refer them to the input, we get twice as much as we had before. And the same thing happens for flicker noise, because again, we have 2 flicker noise sources here and here, and they add up because they are uncorrelated. So we can draw a general conclusion. For a differential circuit, what we can do is define the input referred noise voltage of half of the circuit, okay, the spectrum of it, and then we multiply that spectrum by a factor of 2 to find the overall input referred noise voltage of the entire differential circuit. So that idea can be applied to this circuit as well. Remember that we found the noise performance of this half, 1 transistor with a current source load. Well, now we have 2 of them, so everything gets doubled. So we go back to what we had before. The thermal noise gets doubled, and the flicker noise gets doubled from the NMOS devices. The flicker noise gets doubled from the PMOS devices, and so on. So the most important point here to remember is that the noise calculation for a differential circuit easily goes back to a half circuit, a single-ended circuit, if we know that at the end we have to double the spectrum, the squared quantities, because we are dealing with 2 halves that have uncorrelated noise sources. That concludes our lecture today. I will see you next time.